here is a second problem on Bernoulli differential equations. To be more specific, this is an initial value problem because we also have an initial condition defined along with the differential equation. Now, the form in which the differential equation is given is not a standard Bernoulli differential equation form. One thing we know is that we have to have a coefficient of 1 on y prime to get it in the standard form. So first thing we are going to do is to divide everything in the equation by ty square. So if we divide throughout by ty square, we get y prime equals 1 over t times y equals minus t square divided by y square. Now we can get this in the standard form by subtracting the term 1 over t times y over to the left and rewriting the second term, negative t squared over y square, using a negative power on y. So therefore, the standard form we get is y prime minus 1 over t y is equal to negative t squared y raised to negative 2. Now that we have the equation in the standard form, let's proceed on with the change of variables. So the change of variables are v equals y raised to 1 minus n, and remember the n in this case is negative 2, so we have 1 minus negative 2, and that implies v is y cubed. And this is easy to differentiate. So v prime is 3y square y prime. And now if we solve this for y prime, we get y prime is 1/3 y raised to negative 2 v prime. And now we will start back with our standard form. So we have y prime minus 1 over t times y is equal to negative t squared y raised to negative 2. And now we may substitute 1 over 3 y raised to negative 2 v prime for y prime. And therefore we have 1 over 3 y raised to negative 2 v prime minus 1 over t times y, and that is equal to t squared y raised to negative 2. And now to get v prime a coefficient of 1, we can multiply the entire equation by 3y squared. So if you multiply everything by 3y squared, we end up getting v prime minus 1 over t times 3y cubed is equal to 3t squared. And now this is almost in the linear form because remember the substitution for y cubed is v. And therefore v prime is negative, or should I say v prime minus 3 over t v is equal to 3t squared. And now we may solve this using an integrating factor. So for the integrating factor, the first thing we will have to do is to integrate this coefficient function negative 3 over t. So if we integrate the coefficient function, we have the integral of negative 3 over t dt, which is simply negative 3 natural log of t, which we may simplify using the properties of natural log as natural log of t raised to the power of negative 3. And therefore, the integrating factor becomes e raised to the natural log of t raised to the negative 3. And using the inverse function properties of a base of e and natural log, all we get back is t raised to negative 3. So our integrating factor is t raised to negative 3, which we will now multiply with the first order linear differential equation in its standard form, that is v prime minus 3 over t v is equal to 3t squared. One more time, the resulting first order equation we had was v prime minus 3 over t v is equal to 3t squared. And we shall multiply this entire equation with our integrating factor, which is t raised to negative 3. Now remember, the reason for multiplying the integrating factor is so that the left-hand side collapses into the product rule as a derivative of the product of v times the integrating factor t raised to negative 3. And so therefore, all we have is d over dt, or the derivative with respect to t of v times t raised to negative 3. And that is equal to, if we simplify the right hand side, we have 3t squared times t raised to negative 3, and that simplifies to 3 over t. Therefore, we may now say that v times t raised to negative 3 is equal to the integral of 3 over t with respect to t. And that is a simple integral to evaluate. Therefore, we have v times t raised to negative 3 is equal to 3 natural log of t plus some arbitrary constant c. Now, using the properties of natural log, we may rewrite this as t raised to negative 3v is equal to natural log of t cubed plus c. And finally, multiplying the equation throughout by t cubed results in an explicit solution for v, which is t cubed natural log of t cubed plus c times t cubed. Again, remember the solution we seek is y, not v. So here we may reintroduce our change of variables. Our original change of variables was v equals y cubed. And so that implies y cubed is equal to t cubed natural log of t cubed plus c t cubed. And so therefore, y is the cube root of t cubed natural log of t cubed plus c t cubed, which simplifies further to t times the cube root of natural log of t cubed plus c. And so this is a general solution to the given differential equation. However, let's not forget that we also have an initial condition, and so we must solve for a specific value of c which satisfies the given initial condition, which is y of 1 is 2. Therefore, if we substitute the value of 1 for t, the value of y is 2. And therefore we get 2 equals 1 times the cube root of natural log of 1 cubed plus c. And solving this equation for c gives us a value of c which is equal to 8. And now to get the unique solution, all we have to do is substitute c with its appropriate value, which is 8, and therefore the solution to the IVP is y equals t times the cube root of natural log of t cubed plus 8.